Today we're going to take our discussion of exponential functions back to something we actually talked about a little bit in our very first unit, exponential growth. It tied into our geometric sequences, but we're going to review that concept today, and we're also going to add the idea of what really happens in banking. I think back in 7th grade, you probably learned about something called simple interest, I equals PRT. To be honest about that, that's not how banks calculate interest. Today, we're actually going to learn how they do it, and it is an exponential function. So to start off today, we're going to go back to sort of a slide that we saw back in September. Exponential growth is when a quantity is growing exponentially. It's increasing by the same percent in each unit of time. So you might remember this function, y equals a times b raised to the x. That's not multiplication, that's an exponent. Basically, the A is our starting amount. So if you put $500 in the bank, or the population of a certain town was 20,000 to start, that would be your A. Your B is called your factor, and if that B is greater than 1, it's a growth factor. You might remember if it's less than 1, it will be a decay factor, which we're going to talk about in our next video. And if it equals 1, the population won't change because you're always multiplying by 1 and getting that same A back. X is the number of increases. It could be years, it could be months. Today we're going to talk about some other possibilities for X. And then Y is your end amount. How much is in the bank after a certain number of years? What is the population after a certain number of years? And down the bottom of the screen, you'll see an exponential growth function. Y equals 1,000. I started with 1,000 of something times 2 to the x. This 2, because it's greater than 1, means the function is going to grow. So you might remember that factor can be looked at another way. It's the number 1 plus a rate. So 1 represents that initial amount. You're keeping that initial amount and you're adding a percent to it. So for instance, if your rate was 4% that you were going to earn each year, you would take that 4% and you would change it to a decimal. So we take off the percent sign, move the decimal to make that number, smaller by 2 places. You're dividing by 100, 0.04, but that's not your factor. You add it to the original population. And this number, 1.04, is called the growth factor. And it means that you will get your original population back added with 4% more. So 1.04 would be your growth factor. So today we're going to learn how banks, like I said, actually calculate interest on money. When you put your money in the bank, you do that not only to keep it safe, but you're hoping to get more money back on your investment. That's called interest. So banks don't use simple interest, they use compound interest, and this will be an exponential function. So let's say you put some money in January, you're going to get a percent of that money added on called interest. When we get to February, it's the bank isn't just looking at your original investment. It's going to look at not only original investment, but the added interest that went in as well. So each time the bank is looking at your bank account to give you interest, the number is getting higher because of the interest that's been added in previous months. And this happens naturally through an exponential function. So here is our basic y equals a times b to the x. Y is going to be the amount that will be in the account after X compounding intervals, and we'll explain that in a second. So it's not just years. We're going to talk about quarters and months in a second. A is going to be your initial amount invested, and in banking, that's called principal. Your growth factor will be 1 plus the interest rate per interval. We're going to explain that in a minute. And then X will be the number of compounding intervals. So there's a lot of vocabulary in there that kind of makes sense after we do an example. So let me move on and do that with you. So let's say that you deposit $500 in an account that pays 4% interest compounded yearly. What is the balance after 5 years and after 10 years? Now, right now, we could have done this problem in September because it says yearly. So we look at our initial amount, which was $500. Our factor is going to be 1 plus the interest rate, which would be 1.04. And then we're going to do 5 years, and then we're going to do 10 years to see what happens to our investment, our account balance. Don't forget, when we write a function, the first thing we want to do is define our variables. So in this case, x is the number of years, and y is going to be your total savings in dollars. And here is the exponential equation. We started with $500, and then we are going to take that $500 with 4% for each year that goes by. So let's do it with 5 years. Just kind of showing you where that 1.04 comes from. The book likes to do this a lot, so I just want you to understand where it came from. And then I go to my calculator, 500 times 1.04 raised to the fifth, and you should see about $608.33. Again, rounding to money would be rounding to the hundredth. Put my dollar sign in. I'm going to do that same function, and this time put 10 years in and see what happens to my investment. And you'll notice this time, after 10 years, I have $740.12. Okay, but what happens in the real banking world is that your interest is usually not compounded yearly. By the way, yearly, they might say annually. That's the same thing. But in this next example, you're going to notice the word quarterly coming in. So this time we're going to put $1,000 in the bank. We're going to get a really nice interest rate, totally unheard of right now, with 8% annual interest, so every year. But notice that it's compounded quarterly. That means that they're going to put the interest in every quarter, and they want to know what will the balance be after 3 years. So the A is still the $1,000, guys. That hasn't changed, but now we have to stop before we move on to finding the factor, because this 8% for the year is going to be parceled out to each quarter. Quarter means 4 times a year. So if we take that 8% and divide it by 4, you're going to get 2% each quarter. So our factor is going to be 1.02, not 1.08, because it's per quarter. Now notice these 3 years. Now we don't want to know, our time isn't going to just be based on the years. It's going to be based on the number of quarters. So 3 years has how many quarters? Each year has 4, so 3 years would have 12, 3 times 4. And now we're ready to set up our exponential function. So the first thing is x is going to be the number of quarters, not years, and y is going to be our account balance in dollars. And our equation is going to be y equals 1,000 times 1.02 raised to the 12th. So basically we took the percent and divided it by 4, turned it into a decimal and added to 1. And then we're going to take this x, which was 3 years, and we're going to multiply it by 4 to get the number of quarters. And when you put that into the calculator, you will see that you will have $1,268.24 at the end of 3 years. Let's try that again, but do it monthly this time. So our initial investment is $1,500. And I'm getting ready to think, oh, I'm going to change this to 0.06 until I see the word monthly. This is for the year. There are 12 months in the year. So I'm going to take that 6%, 6 divided by 12, and that's the piece of the interest rate that each month is going to get. Let me show you what I mean here. So I take the 6 divided by 12 is 0.5%. Take off your percent sign, move the decimal 2 to the left, add it to the 1, and that's my factor. Be careful not to put 1.05 here. That would mean 5%, not half of 1%. Now for the x, I've got 5 years, and each year has 12 months. So how many months are in 5 years? 5 times 12, which would be 60 months. I'm going to set up my general equation here. I'm going to define my variables. X is going to be the number of months, and Y is going to be the account balance. my general equation would be y equals 1500 times 1.05 raised to the x. And in this specific example, I want 5 years of 12 months, so 60 months. Put it into the calculator, and you should be seeing $2,023.28. So that was compounding quarterly, compounding monthly. Sometimes you can see semi-annually, which would be 2 times a year. But again, the rate gets divided by how many months. So 6 divided by 12. And the time element, the x, gets multiplied. Okay, so this one is what I call a backwards problem. This time, it's the idea that you want to buy something that you don't have the money for right now. And so you're trying to figure out how long will it take to get the money that you want. This is often could be if you were buying a house, for example. We're going to start with a smaller number than that right now. How much would you need to deposit in an account? It pays 3.5% compounded yearly, so no monthly, no quarterly. This is the easy one. It's just a year, to have a balance of $400 after 6 years. So what is missing in this case isn't the Y, it's the A. The A is the unknown, and that's the one we need to find. The $400 is what you want at the end, so that's your Y. Now I have 3.5. I'm going to change that to a decimal, add it to the 1 to make it a growth factor. And in this particular case, it's 6 years. Remember, there's no quarters, monthly. We're not talking about that. We're at an annual thing. So now, again, I'm going to create an exponential equation. So I'm going to set up my variables as x the number of years, y is the total savings in dollars. I'm going to substitute appropriately into the exponential general function. Notice that a is missing. So right now I'm going to take the 1.035 and raise it to the 6th power. It's about 1.23. This is a one-step equation, so to get rid of multiplying by 1.23, I'm going to divide both sides by 1.23. And when I take 400 divided by 1.23, I will need to put $325.20 in the bank today to have $400 in the bank in 6 years at that interest rate. So that's what I call a backwards problem. I just want to go back and remind you that it's not all about money. So back in September, we also talked about populations growing. So here, population of community has been increasing 20% each year. If the original population was 12,000 people, what will the population be in 10 years? So if we take a look, we're going to define our variable as x being the number of years, y being the total population, and we're going to put things in appropriately. So A would be 12,000, B is going to be 1.2 once we take that percent off and move the decimal 2 places, add it to the 1, and then our x is going to be raised to the 10th, and you would see when we put it in the calculator, it's 74,301 people. This is kind of an interesting problem right now, facing what we're facing in the news today. You know, if we look at exponential growth, you can see what happens very quickly in 10 years here. Imagine if we're talking about 10 days and you were talking about a virus or something like that. You can see how fast something can grow. Thus the discussion about, trying not to have that exponential curve take off. Excuse me. And that's why we're home right now. Last one I want to do today is a population of 20 rabbits released into the wildlife region. The population triples every year for 5 years. What is the percent of increase? So now we're looking for that R. We have to think about that. And then once we have it, we're going to talk a little bit about the population after 5 years. I just want to mention that when something triples, what is happening is you have the original population, that would be your 1, that's your 100%. And then you would actually be adding 200%. And if you take the original 100 plus the additional 200, there's your 300% or your tripling. So your what is your percent of increase? It's actually a 200% increase when something triples. All right, let's go back to our y equals a times b to the x. Our a is 20 rabbits. In this case, we're going to be tripling, so our factor is going to be 3 raised to the x. Oh, let me get it down here. There is our general. And again, don't forget, anytime you write an equation, it should have the x in general, and then you're going to substitute in with the specific in just a second. This case, number of years is 5. So those 20 rabbits, if they triple every 5 years, they will be up to 4,860 rabbits in 5 years. So today, that's a little bit of discussion about exponential growth.